Hi, I'm Joshua Lee, and in today's video, we'll be learning about the Heisenberg Uncertainty Principle. The uncertainty principle is a revolutionary idea in the field of quantum physics. In simple terms, it says that you cannot simultaneously know both the exact position and exact velocity of any object. Well, why is this true? Well, to understand that, we first need to learn about the wave-particle duality of all objects. Everything in the universe, an apple, a cat, and even the computer you're watching this video on, acts as both a particle and a wave. So what does it mean to act like a particle or a wave? Particles exist in a single place in space at any instant in time. On the other hand, waves can exist in multiple places at once, rather than just a single point, since there are disturbances in space. On a wave, we can also identify its wavelength, which is related to its momentum, as seen in the equation P equals h divided by delta. In this equation, P is the momentum, h is Planck's constant, and the delta is the wavelength in meters. Now, Planck's constant is a value that is used to relate a photon's energy to its frequency, but for now, we'll just say that it's a very small value. In this equation, you can see that the wavelength and the momentum are inversely proportional, which means that as one value increases, the other value decreases. Most objects in our daily life have relatively large momentum, which corresponds to an incredibly small wavelength. This is why we don't often see wave behavior from macroscopic objects. On the other hand, microscopic objects like photons and electrons can have wavelengths large enough to detect and measure. So if we have a wave, we can measure its wavelength, which we can use to measure its momentum. But a wave still has no exact position. We can find out a particle's position, but it doesn't have wavelength, so we don't know its momentum. If we want to know both the exact position and exact momentum of an object, we need to combine wave and particle behaviors into a single graph. This would look like a wave, but in a restricted area. So how do we create a graph like this? Well, we can by adding multiple waves together. Thanks to a phenomenon known as wave interference, some parts of the waves add up to create larger waves and other parts cancel out. So we see some regions of waves separated by other regions where the waves canceled out. The more waves you add, the narrower the wave regions become. If we add enough waves, the regions of waves become a wave packet. This is a quantum object. But in order to get this quantum object, we have to give up our certainty of both its position and momentum. Its position isn't just one single point. The object could be anywhere within the range of the wave packet. The momentum also isn't restricted to just one wavelength. We had to add multiple waves to get the wave packet, so the quantum object could have a momentum corresponding to any one of those waves. If we want to be more certain about the object's position, in other words, reduce the position uncertainty, we have to add more waves. Adding more waves will make the wave packet smaller, so now we are more certain about its position. But because we added more waves, we are also less certain about its momentum now. If we want to be more certain about its momentum, we have to add less waves, which means a bigger wave packet and less certainty about the object's position. This is the Heisenberg Uncertainty Principle. The more you know about either the momentum or position of an object, the less you know about the other. The Heisenberg Uncertainty Principle is often confused with the observer effect. The observer effect says that subatomic particles will act in a certain way, but once you try to observe them, it starts acting differently. This is most likely because the method we use to measure these subatomic particles affects how they behave. But the uncertainty principle and the observer effect aren't the same. The observer effect only applies to objects that are directly being observed. But the Heisenberg Uncertainty Principle applies whether an object is being measured or not. The Heisenberg Uncertainty Principle is a fundamental property of the universe and the result of a wave-particle duality of all objects. In today's video, we learned about the wave-particle duality of objects and the Heisenberg Uncertainty Principle. I hope you enjoyed this video. Please subscribe and thanks for watching.